Hello everyone, welcome back. Till last class we were discussing flow inside the nozzle, and if we looked at the discussion, we did not complete the full range of Pb by P0 values we could go to, and we said that we will deal with the remaining later. If we looked at that particular plot of P by P01 plotted with x, and we say this is my exit plane, this is my throat line, we did this and it went up. I am not drawing it really nice to scale, maybe I will make it a little better, it looks more like this. And we said that if there is a shock at the exit, it will be here. This is the throat condition, so this is my P critical 1, P critical 2, and if it comes out straight here, P critical 3. We did all this, and then we said that if I decrease my pressure below this value, this particular region is called under expanded region. If it is in this region, it is over expanded region, and since previously we were interested only in pressure profile inside the nozzle, we said that anything below P critical 2, my pressure inside the nozzle distribution will never change, it will always be this particular curve. We said this and we were seeing plots of it also, and we discussed what will it be if P0 is changing and keeping Pb constant, etc. Those are all just variants. Maybe I can change both, maybe I will increase both, or I will decrease one, increase the other, whatever, I can do so many variants of it, any of them I can do. Okay. If I think about those variants, everything can be normalized to P by P01 and it will fall on this particular curve. Okay. Now we said up to here we have solved the problem, from Pb equal to P0 all the way down to here we have solved. And I also gave you a very special case that if Pb equal to Pc3, then also I can solve it, critical 3. That is, the flow is fully supersonic and it comes out also as supersonic jet, that also we discussed. We have left out a huge range of pressures here just below Pc2 all the way down to 0 pressure value, which may be very low, and except for this one point Pc3. We have missed a whole range of regions, and we called this region over expanded and below this region under expanded. Over expanded and under expanded jets, I called it. Okay, the nozzle is such that when it comes out, this region is over expanded and this region is under expanded, and we said that only change will be outside the exit plane of the nozzle. Okay. So up to from Pb equal to 0, Pb equal to P01 till Pb equal to P critical 2, everywhere this is what is happening. Oh, I am confusing here, it should be P critical 1 divided by P01 here, because I am plotting P by P01 as my axis. It should be non-dimensionalized everywhere. Okay. Anyways, so if Pb equal to P critical, Pb equal to P01 all the way to Pb equal to P critical 2, everywhere I have already solved this, and we know that up to P critical 1 there will be no shock inside, completely isentropic. After that there will be a shock inside, and after that it will become subsonic and it will rise up to that pressure, and there will be a point where the shock comes to the exit. After that we said there is no change inside the nozzle. Now we are outside, we want to solve for this region, this extra region here, over expanded cases. I already told you the change is only outside, so we are going to talk about the jet coming out from the nozzle. From now on we will not consider whatever is happening inside, it is all done, all old history for us, we know how to solve it, we have already solved one example numerical problem also, we will say that is easy to solve. Now we will look at the remaining portion. I want to look at some nozzle, we know we are solving it 1D, so I do not need to worry about shapes being symmetric or anything, it is just 1D problem. This is my exit plane, and if my PB equal to P critical 2 PC2, then what will I have? I will exactly have a shock at the exit and the flow will be just going straight. I have also done one more thing in my drawing this nozzle very carefully. I have drawn it such that the flow is going to be one angle only. Okay, I have made both the edges parallel to each other. Otherwise, if I have a nozzle that is more like this, now the flow here will go this way, flow here will go this way. I do not want to be thinking about 2D problem. So, I will not be worrying about all this. I will just assume my nozzles will look more like this. Exit will be always parallel. Okay. If I think about this, I do not need to worry about that particular aspect of not 1D kind of thing. It is always 1D in my opinion. We are solving only 1D gas dynamics as of now. So, my jet is going to be just parallel to whatever is incoming, except for before the shock it is supersonic and after the shock it is subsonic, exactly same mass flow rate that you know, and so it just goes out as a straight jet. And we assumed one more special thing, we are in inviscid gas dynamics. Okay. So, there is outside air and it is stationary and this gas is going with some reasonably high velocity. I have to draw arrows such that these are longer and these are shorter. Okay, we know high speed flow becomes low speed flow here. Okay, and the pressures are matching exactly. So, no fluid element is going to push the next fluid element, right? Pressures are equal across these two, across this line. So, this fluid element is happy that this pressure is the same as this. So, no force exerted, or both are equally applying force one against the other, nothing goes wrong. Nobody is able to push against anybody, both are equal force. Okay. But we are neglecting this aspect of this fluid element is moving fast and the other fluid element is not moving. Because of that, there will be this aberration, the shear, which we are neglecting here. Currently, we are going to say there is zero shear stress. We are going to assume inviscid flow, okay, because of which this jet will just be a straight jet without any question, no trouble. Life is very simple for the jet, it just has to keep going straight forever. Okay. Why is it just going straight? There was some region where there is high mass flow rate injected into some region where there is no flow. That region wherever there is higher mass flow will just keep moving like that. In reality, there will be some viscous shear stresses developed in this region, and so this region will become slower, this region will move faster. And so, you are going to develop this whole dotted line region is called the shear layer, region where there is shear forces important. Okay. I said important, I am using careful words. Even other places there will be shear stresses, we can neglect it compared to other forces like inertial forces. Okay. That is the only difference there. Anyways, that is too much of fluid mechanics for today, we will not want to go there. We will still assume inviscid. The other special cases, I have this nozzle and I am having PB equal to P critical 3. If this is the case, again there will just be a straight jet going all the way straight, no troubles, same area as the exit area everywhere, and we said inviscid flow is just going to go straight. The only difference now will be whatever is the velocity here at the exit, it will be the same value here. Why is it the same value? I go back to this curve and I see there is no change between PC2 and PC3 up to the exit, it will be the same here. So, I am going to say, and there is no shock at the exit this time, it will be the same on the other side. Ideally, I am supposed to draw all arrows exactly equal length. Okay. It will be the same velocity here also, and it just keeps going forever like this. While in this case, that velocity vector has decreased in length when it goes across the shock. It should decrease much more than that if you think about it, but it decreased at least for me. Okay. So, what happens in between this case and this case? Let me erase all these disturbing things. The shear we will assume is not there for now. We will get back to this after finishing jet flows. We will add shear to the problem after that. Okay. And I will remove these two fluid elements also. So, if I look at this, I have this at P critical 2, I have this when I decrease the PB to P critical 3. In between what happens is our discussion for now. What should happen? Here the pressure is low, across the shock pressure becomes high. We said this flow is over expanded. Go back here. Why did we call it over expanded? Because the fluid at the exit of the nozzle is at a lower pressure. It has expanded too much inside the nozzle compared to whatever we expect. Say I want this line here, I expect this pressure, but it has expanded too much to much lower pressure. That is why it is called over expanded. Okay, it will be very confusing when you go to propulsion and you talk about rocket is going up, pressure is decreasing outside, but I call it going under expanded operation. Okay, it will be opposite if you think about it, but actual explanation is coming from the point of view of fluid sitting inside at the exit of the nozzle. That is the only way we define this over expanded or under expanded. I am going to say this fluid is much more expanded than what is needed for the outside world. So currently it is over expanded condition. Okay. That is what I am going to look at. When I look at it this way, what should I need to make the pressure go up? It should be a set of compression waves, and typically we will say that compression waves bunch together and form a shock. We will keep it that way for now. I have not given you complete proof yet. Okay. We will go to shock tubes and deal with that later. That is towards last part of the course probably. Okay. So we need some kind of shock. If I think about simplest thing, say I am very close to this P critical 3 and I am increasing my pressure here slightly, what kind of shock should I have at the exit? Only thing possible is oblique shock. There is no other choice for you. Why? If it is a normal shock, that is the other possibility you have. If it is a normal shock, then it is too strong and it will make it to go to P critical 2, that kind of exit pressure. But we want much lower than that. We want pressure lower than this, but more than this, that kind of intermediate value. So I cannot have a strong shock like a normal shock. I can have some other shock. Okay, we can have so many other combinations. We will just think about simple situation right now. So an oblique shock. So I will draw a case where my exit will have an oblique shock. Okay. Can it be an oblique shock like this in my jet? This oblique shock will meet the pressure this side. Oh, by the way, if there is an oblique shock like this, what will be my flow direction? Which way? Will it go down or up? Fluid will go down. If there is a shock like this, then my jet will be doing this. Okay. If my shock is like this, how do I know this? Go back to the fundamental problem we had. If I have a wedge like this, my shock will be like this, flow goes like this and it turns this way. That is the same region. This region is what I am talking about here, that region. If I think about it that way, if I have an oblique shock like this, then the pressure here will be same as the pressure and the back pressure here. Is this the correct flow situation? Direction is what? Direction has changed, as in it should be the other way you are saying? Direction of the jet should be straight, you are saying. Okay. That is not the most important way I want to look at it, but yes, final correct thing will be direction of jet should be straight, but not right now. There is some other mistake here. What is the mistake? At the bottom line, the pressure here is same as the pressure here. There is no shock here, which means the pressure here is same as exit pressure, but outside world we told is a PB greater than exit pressure. That is why it is under over expanded jet, right? It is expanded too much compared to this, which means this pressure is lower, which means currently I have a layer where pressure here is higher than, I will draw with hatch, pressure here. That is lower pressure, this is higher pressure. What will happen? Naturally this fluid element will push that fluid element up. Along that border there is unequal balance, right? One guy is pushing less, other guy is pushing hard. Then the boundary will move. What does that mean? This last fluid streamline is going to turn inward, we said this fluid element turns this way. Why? For the same reason that side, and so it formed the shock. Now I am going to say for the same reason here this fluid element will turn inward, and for this to happen there should be a shock sitting. I will draw it much more clearer now. I am going to say this fluid element wants to turn this way. To make it happen there will be a shock like this, okay, that is supposed to happen. Now that it is getting too much confusing, I will draw this nozzle with red only near this portion. Okay. So this white thing is my shock, okay, and so both the fluid elements are turned inward, which means now my final streamline, the jet boundary, that streamline is going to be turning inward, right. What does that mean? My jet, say I think of that jet as one slab of fluid here. That slab of fluid as it goes in is getting shrunk. Is that logical? Is that supposed to happen? The slab of fluid when it is coming out is now getting shrunk in size. Is that logical? What is the reason for it? No reason. What is the reason? Why should it be shrunk? Because of exit is not very clear, because of increase in pressure, because of increase in density, yes, because it is getting compressed, okay, that is the idea of the shock anyway, to make the pressure go higher, okay, because to make the pressure go higher it has to be compressed. The size of the slab also should be lesser as I go there, right. I am thinking about one slab of fluid going like this, it is increasing in size as it goes here. Why does it increase here? It is expanding, it is increasing in Mach number, and when it goes here it is suddenly having to change in size here. All this time we talked about one Mach number at each location axially. After exit I cannot talk about that. Why? Because the 2D problem, I have introduced a 2D component here. Oblique shock cannot be a 1D problem, it is a 2D problem. So now I am going to talk about inside here one Mach number, above the shock there is another Mach number. That is the best I can do now. Okay, it is already 2 components at every section I think about. Okay. So the idea of this is this. Now I say I increase my back pressure a little more, what happens? The shocks have to be a little more strong. Okay, if the shocks have to be strong, I will draw the picture again here separately. This is my nozzle, looks like my chalk writes very thin. Maybe I will draw this is white only, you guys can manage. It will become lot more strong, and the jet boundary will be shrinking faster, okay, that is what will happen. If you think about the case before this must have been this, where the normal shock is there, jet is going very straight. Immediately after that if I decrease pressure some more, it jumps to this case where it is shrinking a lot, and then when I decrease further it goes to this case where it is slightly expanding, and eventually it will reach this case. How does it reach this case from here? I keep on decreasing my pressure, back pressure, it is going to tend to PC3 eventually. Back pressure is some value here, I decrease back pressure, what should happen here? My oblique shock should be less angle, beta will decrease, okay. When will it become this case? Do not talk about the PB now, tell me something about the beta. Beta will not become 90 degrees, beta will not become 0, that is why I asked this question. Beta will go to mu, the Mach angle, that is the weakest shock you can ever have, right. Beta will become mu, that is a specific reason why I asked this question. In fact, if I draw that particular beta here, it will just become that Mach wave which will just tell the fluid not to change anything, right. We always talked about Mach wave as a wave that says stay as is, do not change, do not increase pressure or decrease pressure. It is a wave that says do not change anything. Okay. So, all this time it is telling compress, compress, compress. If I increase my back pressure, it tells compress more or compress faster. When I go decrease, it goes to a point where it says do not change. There is a point where it will say do not change. This whole sequence happens in here. Okay. Of course, I have not drawn it the correct way, this picture should have been in here. Okay. That is the full normal shock. It becomes high angle oblique shock to a lower angle oblique shock to eventually becoming Mach angle. This is the whole thing that is going to happen as I decrease my back pressure. It is going to tend to this finally. We will talk a little more about this between this last picture and this picture after some time. Okay. We will look at what happens in this region. We will draw a much bigger picture now. This is my full nozzle now. This is my full nozzle and I am having an oblique shock from both sides. I just wanted to draw it slightly wavy, okay, so that you remember that this is a shock. Ideally you should just draw straight lines because in real life it is a straight line. Okay. When you see pictures from experiments, it will be a straight line really. Okay. Now fluid element here is coming at this angle and because of oblique shock it is turning like this. Same thing here and it is turning like this. And so my jet boundary is going to be parallel to these vectors, post shock vectors, something like this. And you can say that the jet, that full slab of fluid which I think about somewhere here has now shrunk to this size here. Of course, I am assuming that the slab does not get distorted, actually it will get distorted. Okay, we will ignore that thing, it just looks like it shrunk. Of course, here it will be more like this, it will be dragging slowly, it will be slightly behind. We will ignore that part right now. Okay. What happens after this point? They are both going to crash into each other. If you look at the velocity vectors here and here, they are going to be crashing into each other. That is not allowed. We already talked about this problem, right. We said when there is one shock that is right running, one shock that is left running. Now we will talk about what happens when they interact. What should I satisfy downstream of the point? Pressure and velocity direction, two conditions, always those two conditions. In supersonic flow typically these are the only boundary conditions, pressure and velocity direction condition. Okay. So now I have to think about drawing some line. I would say on this side of the below the line, all the fluid from below will go this side, above will be all the fluid from above. Typically if it is a symmetric problem, that will be the line of symmetry anyway. Since fluid mechanics has a lot of line of symmetries, we will just keep it line of symmetry as a horizontal axis for us. So the fluid that is coming at this angle has to now turn back to become parallel to this axis. To do that, there will be another oblique shock. Okay. And then the flow here will go straight. Similarly, exact symmetric problem, so I will just go this side. Of course, it looks like I have not drawn the jet boundary symmetrically. I will adjust that. Okay. And then this side also it will go straight like this. Okay. This is for a simple system. Now what if I increase my back pressure a little more? What will happen if I increase my back pressure? This angle will go increase higher. Okay. Let us say I will use, I have one more color here, I will use green, I think it will work. I will draw another sharper shock. If this is the case, then it is a stronger shock, which means the jet will shrink much faster. I am drawing everything on green on top of the other one. Something like this, and these shocks now will send the flow more strong against each other. but remember stronger oblique shocks will have much lower Mach numbers downstream of it. So, the Mach number downstream is lower compared to the previous downstream Mach number, and the angle that it has to turn by is now higher, right. A weaker Mach number flow has to turn high amounts. Sometimes there will be a point where it will not be possible for it to turn by a attached shock. What happens at that point? We will go cross that theta beta m curve. Okay. If it is a weaker Mach number and I want this strong thing to happen, it has crossed. So, what happens in that situation? It becomes a Mach reflection. That is what I want you to think about now. Since I have introduced you to the other simple thing, now you can think about a Mach reflection. Along this dotted line, there is going to be this Mach reflection happening out there. Okay. So, if I go even higher pressure, I have one more color. I have so many colors here today, I will just use all colors. So, I take blue and draw one more. Now, I do not need to draw the angles, vectors, everything you know, I will just draw the new shock point. New shock will look more like this. Okay, it will look more like this. And if I have one more color, if I draw one more slightly higher PB, then I may have this. If I increase any more, let us say I reach my back pressure original PC2, then I will just have one straight shock out here. So, if you look at it, shock is doing a continuous change. Okay. If I think about PC2, my shock is sitting on the exit like this, white. If I decrease it slightly, normal shock is almost normal shock most of the places, only some portions it is oblique shock, which means only those regions the pressure is lesser, other regions it is roughly the same as this original whatever exit pressure. Okay. So, on an average this fluid element has shrunk, this slab of fluid has shrunk on an average. Okay. When I decrease pressure more, it needs lot more change. So, it goes to a point where the more of oblique shock is happening, less of normal shock is happening, and it just continues like this. Eventually there will be a point where there is no more normal shock, the whole thing is oblique shock. Okay. And beyond this point I keep on going, let us say I will again start using colors. I go again and I will start using orange, I will go in the same order. If I decrease pressure further, then my oblique shock may become this. Oblique shock may become this. There will be a point where if I decrease further, my oblique shock will become so weak that it will be just a very weak wave, my Mach wave. This whole thing happens as I go from PC2 to PC3, the whole sequence goes through this whole sequence. Someday I will show you a video of this whole shock moving slowly out and forming this X like shape. Okay. It is a nice thing to see, it is fun to explain it better than just watching it. Okay. Anyways, so this whole sequence happens. Okay. During this whole time, what happens to my jet boundary? More difficult question to ask. At the exit, if there is a shock, then we know it is like PC2 here, it is just going to go straight, no change. When it is just a small shock in that small region alone, what should happen? I will take that small region and draw it better so that you can see what is happening there. This is my nozzle exit edge, one edge only I am showing. There is a shock and that is reflecting like this with a normal shock here. If this is what is happening there, locally the fluid boundary is this. I will erase the extra things. Okay. And below this line fluid is just seeing a normal shock, it just jumps like a normal shock. The remaining regions is going to come straight, turn like this and go like this. If you see this beauty of nature being symmetric or very continuous, all that is seen here. When we discussed before, we said that when looking at all these pictures, we said that it was going straight, suddenly it went to shrinking too much and then it shrinks lesser and lesser, becoming parallel again. That never happens in nature, nature is never discontinuous. Okay. If you think about it, what is really happening is between this picture where there is a shock at the exit to an oblique shock, there are so many of this sequence, orange, blue, green, like that, where it goes slowly from being straight to a little bit of curved, okay, a little curve, and then when this goes more to blue, it will be a lot more, and when it goes to green, it will be a lot more, and eventually there will be a point where it will become something like this white, and then it will go along with whatever we already thought about. So it is very continuous. Okay. Nature does not like discontinuities. Okay. There is always some mechanism in nature which gets rid of any discontinuity in life, similar to it does not like any singularities. Okay. Anyways, that is one part of the thing. Okay. How do I think about this in another form? I have drawn all these shocks, but I said that specifically I have drawn this particular shock, it bounces off this way as a Mach reflection, and I stopped drawing the shock just outside the final streamline. Why did I do that? That is the next question. I am slowly getting you involved in every detail of the problem. Okay. So when I look at that, the way I want to look at it is I will take a simpler case where this is my exit plane and there is an oblique shock, there is another oblique shock, and I want to think about it as each of these shocks are some wave which is carrying a message, right. This is how we did it in 1D shock moving shock problems. We said if I suddenly close a door at the end of the pipe, the shock travels telling the pipe closed, that kind of thing. Currently what is going to happen is there is a slab of fluid, it is coming with some reasonable velocity, and suddenly we are seeing when the slab comes to the exit, this corner is seeing higher pressure. Why higher pressure? It is over expanded jet, this is over expanded compared to the outside world. Okay. So this pressure is higher than this inside, so it is seeing a higher pressure. What is it? It is suddenly pushing, it is like a piston suddenly pushing against the fluid slab there. So there will be a shock that is forming, and what is the job of each of these shocks formed? They have to go and tell all the fluid that there is a pressure jump there. Okay. Any wave created has to be telling information to all the fluid element as much as possible, till it loses its energy it will go and tell. Okay. It is not lazy, life is very nice for those people. Okay. Our messengers may take break and all, they do not, they just go continuously, no stop, okay, till they lose all their energy, they just keep running. Okay. In this slab it is just having to run straight from that corner to this corner, because that is all the fluid that is having this action. Okay. So what will it do? From that point it has to go all the way through, it cannot stop halfway. Why can't it stop halfway? This fluid came to know that the pressure has to be increased, this fluid also came to know that the pressure has to be increased, because this guy went up all the way by the time I reach here. That same fluid slab, when it is here, both the shocks are at this location, one is running this way, other is running that way. Okay. Should I stop there? They do not know, messengers are supposed to be purely messengers, think about it, they cannot think for the kings. Okay. They are supposed to carry the information and tell everybody in the whole world, they are not supposed to be thinking halfway, they just do their job, they are just going to go across and just keep telling increase pressure by so much, increase pressure by so much. Because of this what happens is the shock continues past that point, and here also the shock continues past this point. So we go to a point where that fluid slab Of course, it has shrunk in size. I did not draw the jet boundary line. So, ideally the fluid element has already shrunk in size to something smaller, because they all obeyed the messenger. Remember, the life is very ideal in nature world. Okay? Everybody obeys the king's orders. Okay? Everybody just does their duty without taking rest in the middle, all that. Okay? These messengers do not take coffee in the middle somewhere, they just keep running across, okay? All that very nice stuff. And finally, there will be a point where this shock has gone all the way to the end of that fluid and just stays there and tells, yes, the pressure has to be increased. Okay? All this point. After that also, the fluid element, that shock sees that there is a fluid outside, right? Ideally it wants to go and tell them also. Okay? All it is supposed to do is, if you see a fluid, tell it to increase pressure. Okay? It is doing it very well till here. When it goes outside, the guy sitting outside, the boundary condition is very adamant. Boundary condition guy is the atmosphere, is going to say, whatever you tell me, I am not going to change my pressure. Okay? So, what happens suddenly is, that messenger is going to be pulled out, somebody else is put in that place who is going to say decrease pressure. Okay? So that the pressure will be the same at that point. Only for that one point, the boundary point, there is a exchange of messenger suddenly. Now what will that messenger do? He has to run, he will again start running, right. He is going to say decrease pressure by so much, and typically it is done by a whole bunch of expansion waves, and they do not go all together, they are like a shock, they go each individually. So there will be a whole set of fan of expansion waves running out. Okay. They are going to go run this way, and similarly the same thing is happening on the other end. Okay. And they will also send out an expansion wave fan like this. There will be a whole bunch of expansion fans created, one from this end, other from that end, they are created and they are going to run across. Why? All because I will label the regions here. This is 1, 2, this is also 2, this is region 3, and E is same as region 1, there is no change here, and from 1 to 2 the pressure has become equal to back pressure, that is the idea of the shock. Okay. Same thing this side, same equivalent shock here, and then because the shock is continuously going past that point, the pressure increased from 2 to 3. 3 is above the back pressure, because atmospheric pressure gas is processed by a shock. Okay. So it is going to be higher than that pressure. Now this higher pressure is not liked by atmosphere, so it is sending out an expansion fan to decrease that pressure. What is going to happen? I already told you the flow vector direction. I will draw one more picture parallel, I do not want to disturb that picture. I am drawing velocity vector here and I am showing you region plot and pressures I am describing here. Okay. Flow velocities are parallel. It is as if this jet has been shrunk to a smaller size jet here. I have come up to that point. Jet has become smaller size jet and they are going parallel out like this. And when the jet comes out of this point, the very first point when the jet like thing comes out, immediately it is seeing pressure outside is lower than the pressure inside. That is another way of looking at the same thing. Okay. One way of looking at it is, the compression wave comes here and sees an adamant atmospheric boundary condition which says pressure cannot be changed. So the boundary is going to replace the compression wave with an expansion wave at that point, so that the compression and expansion gets cancelled. Okay. At that point alone they will be cancelling, everywhere else it is going to continuously expand. That is one way of looking at it. Other way of looking at it is, it has got compressed and now I have a new jet going out like this. okay, as if it is a shrunk jet coming out, and that jet when it comes out immediately it is seeing the pressure here is higher than the outside pressure. What should it do? It has to expand. Okay. So, there will be expansion fans here, and the fluid element goes out. Of course, you know expansion also adds to it some velocity vector component, so it is going to turn out. So, because of that my jet boundary is going to increase again. I am not drawing both the pictures exactly the same, but you understand the idea. I have not drawn the same expansion angles. Now, because of this, the region 4 here is also going to be atmospheric pressure. Okay. Region 4 here is also going to be atmospheric pressure. And how far will these expansion waves run? They will run till it goes and hits the other boundary. Okay. Till the time no conditions. So, it will just keep on going till it reaches the other boundary. What happens when an expansion wave goes and hits a boundary, which is again adamant, it is going to say the pressure has to be fixed. Expansion tells I have to decrease pressure. So, it will be replaced by a compression wave which will tell increase pressure. Why is it a compression wave versus previously it was a shock? It is just one wave, one expansion wave going, it needs to be replaced with one compression wave. While here there was a whole bunch of compression waves together coming as a shock. So, they all have to be replaced by a whole bunch of expansion waves together at that point, and they are all running at different speeds. So, they are separating out. Okay. That is a way of thinking about it. So, at every point there will be a compression wave forming, there will be so many compression waves like this forming overall. What happens when a whole bunch of compression waves come together? They will eventually form a shock. They all come together and form a shock there. Okay. And this picture seems to be a little nicer to draw, so I will draw this one here. It is smaller, and I will draw my initial axis, okay, and they will form a shock like this. Same thing will happen on the other side. They will all form a shock together. I think this picture is nicer than this picture. Let us just look at this one. And again now I will mark my region 5. Okay. Now what happens? All these compression waves came together, formed a shock, and that shock is running through. It cannot stop halfway, it has to go all the way till it finds somebody adamant who will replace them. Okay. So, they will keep on running again. What happens here? The flow was going straight. Oh, I have to draw the angle. This vector that is going up is now going to see this expansion, which is going to tell pull it that way. So, it will become parallel again. Okay. Going straight flow is going to see the shock and it is going to turn down. That will happen here. So, my jet boundary will come in again. This will happen there. Okay, from now on I will not draw anything on the bottom picture, I will just keep the top picture. Okay. After this, what should happen? Shock goes and hits a boundary, expansion should start. If I look at it, that same thing happened here. Shock went and hit the boundary and immediately expansion started. So, what happens is this whole sequence from 3 to, I did not mark this region, this is 6 and this is 7, 3 to 7, the whole thing, that whole region I am going to capture and paste it again there, take and paste the whole thing there. So, I will have that whole cell forming here. Okay. If I look at what is happening inside, it is a whole bunch of expansion fans turning back to compression, forming a shock and crossing to that side. Same thing here, whole bunch of expansion turning back to compression, forming a shock and going to that point. That whole sequence happens again. If I want, I can label them again. it so happens that if we are in very ideal world, the pressure at 3 and pressure at 7 will be the same. If I do not have any other losses, it will be an exact repetition, okay, and it just keeps on going like this. It just goes up, comes down, goes up, comes down, goes up, comes down. Okay. If you think about it, it is like some new driver driving a car. Okay, they want to supposed to be going along one straight line. If they got one disturbance, they will correct for it for going here, they overshoot, go that side, and then they correct for it, go this side, overshoot this side. They just keep overshooting. When you are very learned, you will start applying brakes when it is going closer. That is not happening here. It always, if you look at the center line, 3 is higher, it becomes atmospheric pressure somewhere inside this expansion, becomes lower, jumps to higher, becomes lower, jumps to higher, just keeps doing this. If I look at any other line, I have drawn so many vectors here. If I draw all of them connected together, it is going to look like this. It is going to be going down, coming back out, going in, coming back out, and it is just going to go some wavy fashion. Okay. If you look at it here, it is going to come straight, go in, go straight, go out, 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 go parallel, go out, go parallel up to here, jump in, come back straight, and it just keeps doing this. If I look at this, in those points there will be a small region where the pressure is exactly correct. That is the pressure it had to achieve, outside pressure. It has achieved it even at 2. If I go along the center line, it really never achieves it. It just jumps up and down above that point, except through inside this set of expansions. Somewhere here it has to cross it slowly, okay, but every other point it just jumps up and down. That is what really happens. Okay. There will be a time when I will ask you a question where I am going to put a pressure transducer somewhere here and I am going to change my P naught in my nozzle. That is a beautiful problem to solve. Okay. I am just leading you into that direction right now. That is a beautiful problem to solve. If you solve that problem, you can solve a problem of a cycle tube being punctured by a pin and put a pressure transducer outside. What will you see? More practical problem to solve. So much things can be done. Okay. Anyways, so we have come to a point where we have discussed to a reasonable extent over expanded jets, that is the cases where exit pressure is too low compared to the outside pressure, too much expanded, over expanded case. Okay. And now you can tell what happens if it is more special case of slightly less than P critical 2 only. Then I will have a case like this. Again the same thing happens here, there will be an expansion fan, and that will go turn around into a compression waves and form another shock. And they will again have this jump typically, and it goes through the whole sequence again. It will again have an expansion, all that. I have not drawn the jet boundary here. If I draw the jet boundary, it will be something like this. And then it will turn down again there. It is not looking very correct at the beginning, but other things are all correct. Just at the beginning it looks like it is going straight, it should actually be coming from much higher heights. It is roughly correct from here. Okay. So if you look at it again, starting from expansion till the shock, the whole sequence repeats after that. Only thing that does not repeat is the first shock portion. This particular thing is called the expansion shock cell. Okay, the same structure repeats again and again. They call it the shock cells. If you think about the temperature of the gas along the center line, I will go back to this picture, it is nice. If I think about the temperature of the gas along the center line, 1 is high Mach number, 3 is low Mach number, 5 is high Mach number, 7 is low Mach number, right, expansion versus shock. So I can tell if it is high Mach number, it is low temperature. So here it is low temperature, here it is high temperature, low, high, it just keeps going oscillating. Okay. What happens because of that? if I have hot gases coming in, the temperature becomes too high here that the gas starts glowing. Okay. This is the kind of glows you will see as diamond shaped glows behind your supersonic jets takeoffs. You would see that SR-71 typical pictures will be available on the web if you want. Just go look at it taking off. You will see these diamond like structures just behind it which are glowing hot. Okay. Typically they will be glowing orangish yellow. This portion will be glowing hot, then the region 7 will be glowing hot, then 8, 9, 10, 11 will be glowing hot, like that it just keeps going. Okay. The other regions will be cold. If you have such a case, then it will be glowing differently. This you can see if you have if you ever seen a rocket takeoff. If you see a rocket takeoff, you will see this kind of situation where you will see this flat portion and then a glow behind it. Okay. Again same thing will repeat for 1 or 2 more times. Okay. This is what you will see. If you are observant, you will also see one more thing, this whole jet will keep on shrinking in size in real aircrafts. We will see why next class. Okay. For now we will stop here. Under expanded jets we will deal with tomorrow, and then we will talk about shear layers. Okay. See people next class.